So this is Physics Chapter 2, chapter on dynamics, lesson 1. In this chapter, we're going to talk about Newton's laws of motion. Newton said, "If I have seen farther than others, it is because I have stood on the shoulders of giants." Sir Isaac Newton, 1642 to 1727. Some examples of describing motion from everyday life. We can distinguish between speed, velocity, and acceleration. We can talk about what is the acceleration of gravity, which we've done in chapter 1. We can talk about how does the acceleration of gravity depend on the mass of a falling object. When we just think about two different objects of different masses or different weights falling, we know that obviously the heavier one will fall faster, even though gravity is a constant at always 9.8 meters per second squared. So we can talk about why some things fall faster than others. We can also talk about how do we know when a net force is acting on an object, and have we ever been weightless or have we ever been massless? The acceleration of gravity we know is a constant at 9.8 meters per second squared. So we know as objects fall, they accelerate, and the acceleration will always be that g equals 9.8 meters per second squared. This means that the higher we drop an object from, the greater its velocity will be when it finally impacts. Galileo has previously demonstrated that g, that's the acceleration of gravity, is the same for all objects regardless of their mass. And this was confirmed by the Apollo astronauts on the moon, where there is no air resistance. So we'll watch that video in class. We'll watch these vacuum videos in class as well. Sir Isaac Newton, perhaps he was the greatest genius of all time. He invented the reflecting telescope, he invented calculus, and connected gravity and planetary forces. Philosophiae Naturalis Principia Mathematica. So, we're going to talk about three different laws of motion brought to us by Newton. Newton's first law is called the law of inertia. This is the law that says a body at rest tends to stay at rest, and a body in motion tends to stay in motion. So in the little animation at the bottom of the screen, the driver of the car is in motion, and so when the car stops, he tends to stay in motion and his body continues out of the car. This is true unless a force acts upon it. So there we see another example. A force, in this case the smaller car, is acting to stop the moving truck. However, there is no force on the ladder to stop it, so it wants to continue moving and goes flying forward. Newton's second law is the formula sum of all forces equals ma. So when a force acts on a body, the object will accelerate in the same direction as the net force acting on the object. So we get this simple little formula that says sigma F, sigma meaning the sum. So the sum of all forces is equal to ma, which is mass times acceleration. 1 Newton is the force required to accelerate a 1 kilogram object 1 meter per second squared. Whenever we're talking about forces, we give the units as newtons, so we label them with a capital N. Newton's third law is the action-reaction law, and this one says for every action there is an equal and opposite reaction. Discussing free body diagrams, we're going to use these a lot in chapter 2. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces. They would be holding it back, so they'd be moving towards the left. If we neglect air resistance, a free body diagram for this situation would look as pictured. So the free body diagram is telling you that the applied force is moving to the right. This is the force pushing the book to the right. It is resisted by friction, which would want to hold it back, meaning friction is a force moving to the left. And then the other two forces we see are the force of gravity pulling it down, and the force of gravity is always counteracted by something called the normal force, and that's counteracting gravity. The reason we have or know that that normal force is there is if there was nothing reacting against the gravity, then that would mean essentially the book or you or anything else would be kind of getting sucked into the earth just because of the force of gravity. So there's the pressure of whatever you're on, standing on the ground, or in this case, the book is sitting on top of a desk, and it's the force of that object underneath them that counteracts the force of gravity and keeps the object from just sinking away. The vector nature of force diagrams. At what rate will this wagon accelerate to the right? So we have a situation where we have a 20-kilogram wagon. There's the force of gravity pulling down on it, but that is counteracted by the ground it's sitting on, which is the natural force pushing up. So we've actually not even written in those two forces because they're perfectly canceling out. There's an applied force of 50 newtons pulling it to the right, and that is resisted by a frictional force, represented by FF, of 5 newtons holding it back to the left. So if we draw this in a free body diagram, we'll have the following picture. A free body diagram always draws the object and its mass, and then has vector arrows showing the different forces on it. So here we have the natural force pushing up, which is counteracted by gravity pulling down. We have the applied force of 50 newtons to the right, and the frictional force of 5 newtons to the left. So if we calculate the sum of all forces, we're looking for the acceleration. So we can simply take our formula and divide the forces by the mass to find acceleration. So the sum of all forces would be the 50 newtons moving this way, subtract the 5 newtons because it's moving in the opposite direction, and divide that by the mass, which is 20. So we get 50 minus 5 over 20 equals acceleration. So then our acceleration will be 2.25 meters per second squared, and that would be towards the right. A slightly more complex example. Consider an object of 20 kilograms that is experiencing a tug of war by 3 different people. So we've got person 1, which is force number 1, pulling with a force of 30 newtons towards the right and 30 degrees up. We have person number 2, force number 2, pulling with a force of 20 newtons, and they are pulling right with 30 degrees down. And then the third person is pulling straight left with a force of 10 newtons. So we can calculate the sum of all forces on this, and we could calculate the acceleration with it by adding up all of these 3 different forces. We can add force vectors just like we added velocity vectors in chapter 1. So in order to add these 3 force vectors, we need to know their x components and y components, because then we can just add all the x values together and we can add all the y values together. So if we look at force 1 to start, we need to know this x component. Which that we could write as cosine 30 is equal to that x value over this 30 newtons. So the cosine here will be this x value over the 30 newtons, which then means x is going to be 30 times cosine 30, and so we get an x value of 26. So for force 1, we know it has a force to the right, a horizontal component of 26 newtons right. And you could do the same thing for the vertical component. So if we said this was y, then we would get sine 30 is equal to y over 30, and then we could calculate it that way. And so we would find that the vertical component will be 15 newtons up. Repeat the same process for force number 2. Find the horizontal component, and we'll find that that's 17.3. And the vertical component, and we will find that that is 10 newtons down. For force number 3, it's pretty easy. It's going straight horizontal, so the horizontal component is 10 left. There is no component pulling it up or down, so the vertical component is 0. If we add those all together, we'll have a positive 26 moving right, add to that a positive 17.3 moving right, and then we'll have to subtract the 10 because it's moving in the opposite direction. And so we get a total of 33.3 newtons to the right. And then for the vertical, it's a positive 15 for this purple one going up, subtract 10 for the yellow one going down. Red doesn't contribute at all, so we just have 15 minus 10, giving us a total of 5 newtons up. Once we know that, we can draw our result. We know we've got a total of 33.3 newtons going right, and we have a total of 5 newtons going up. We can then use those to draw in our resulting vector, and now we can use Pythagoras to figure out what that resulting vector actually is. So we've got 33.3 squared plus 5 squared, which gives us 33.7 newtons total. And then we can use one of our trig ratios in order to figure out that theta. So tan theta is 5 over 33.3. Using inverse tan, we then find that theta will be equal to 8.5 degrees. So our final net force is 33.7 newtons going right 8.5 degrees up. Now, if we want to know what the acceleration is, we have to remember that the sum of all forces will be equal to mass times acceleration, F equals ma. So we know that the sum of all forces is 33.7 newtons. That's what we just calculated. And we have this formula, sum of all forces equals mass times acceleration. So 33.7 will equal 20, that's the mass, times the acceleration. So to find acceleration, then you can just divide both sides by 20, and we'll get the acceleration is 1.7 meters per second squared. That is going in the same direction as the sum of those forces that we had on the previous slide. So the acceleration will be 1.7 meters per second squared, going right 8.5 degrees up.